Hello, my people. Hope we're doing well. This is video 2 on the volumes of solids with known cross-section. This worksheet, you've seen it before. You actually asked me to do number 7 off of this one at the end of our time on Tuesday. But I figured that we might just go ahead and walk through a lot of these. Now, all the ones on this sheet are perpendicular to the x-axis, so we'll just sort of keep that. But they do define different areas, and they do have different cross-sectional shapes. And since we now have a good idea of where those constants come from for those cross-sectional shapes, and the fact that those constants can be plopped out in front of any of these integrals, it ought to be pretty smooth sailing from here on out. So let's go ahead and let's do number 1. Okay, it is the region y is equal to 4 minus x, y is equal to 0, and x is equal to 0. Now, let's go ahead and scale it the way we're used to scaling it when we have no reason to do otherwise. Each box being each 2 boxes being worth 1 unit. We will go ahead and draw the y is equal to 4 minus x, because that's negative x plus 4, right? Let's go ahead and color code these just so it's real easy to see. I see the fact that, that right there is that. Y is equal to 0, being the x-axis, is here. And then, of course, x is equal to 0, being the y-axis, is here. And this region right here being the base of our solid. Now, the next 2 things we need are the shape of the cross-section, and this one was simply squares. And we need the axis which they are perpendicular to, or to which they are perpendicular, or whatever. And that means that those cross-sections wind up being here, okay? Now, we know that those cross-sections are squares, so they all, in various sizes, represent something like that, where they sort of stand up off the paper, and they'll get increasingly smaller, all the way down to disappearing down here at x is equal to 4. And I know that because they are squares, they have a coefficient or a constant sitting out in front of the integral of 1. I know my limits of integration run the width of my region, which goes from 0 to 4. So this one actually ought to be relatively straightforward. We go 0 to 4, just to be, sure, I'm going to put my 1 out in front. Now I need a representation of this height. Well, it's the same logic of, the height of each of the cross sections, the rectangular cross sections, when we are finding the area under the curve. That is like basically how I represent this right here. It's still the same logic. It's just this function right here. And so 4 minus x is my s of x, right? That becomes my s of x. And of course, I need to square it, multiply it by my differential, because that is my width of all of those cross sections, right? Because it is an infinite number of cross sections of infinitesimal width. Now, this one winds up being really straightforward. There is a reason why it was number 1 on the worksheet. And it foils out into a perfect square trinomial. And of course, I did it in descending order like this because 4 minus x squared and x minus 4 squared are the same thing. Because if you pull out the -1, the -1 would be squared as well. And basically, a minus b and b minus a are negatives, but the negative gets unnegativized when you square it, right? And so when I integrate, it becomes 1/3 x cubed Now x becomes x squared over 2, so 4x squared, and then 16 simply becomes 16x, and that goes from 0 to 4. That means that I'm going to have 64 over 3 minus 64 plus 64, right, minus 0. Now, those obviously cancel out, okay? And I'm left with an answer of 64 thirds. And just in case you're curious, did Mr. Ford make an arithmetic error? Well, let's go ahead and see. Let's go ahead and do the integral from 0 to 4 of 4 minus x. Now, if it were a more complicated function, I would probably go and plug it into y1 and basically put, instead of 4 minus x, y1 right there. That's 21.333333. And if you want to see it in fractional form, you do alpha f1 and you go down to option 4, and that basically takes your answer from fraction to decimal or vice versa, and it winds up being 64 thirds, just like we got right here. Okay. Now let's go ahead and just keep marching through examples. The next one that we have is going to be, it's going to have the region bound by y is equal to 4 minus x, yes, again, y is equal to 2 minus 1/2 x, and x is equal to 0. Okay? The cross sections in this case are semicircles. Okay? Semicircles, of course, have that pi over 8 constant that sits out in front. I'm going to be going perpendicular to the x-axis. Again, let's go ahead and scale it the way that we are used to scaling it when we have no reason to do otherwise. Every 2 boxes is 1 unit. That means our Cartesian plane goes from -5 to 5, -5 to 5. Okay, 4 minus x, as we did last time, looks something like this. Okay. Now, 2 minus 1/2 x, okay, is actually going to wind up starting here and going down like this, and actually meeting here at that same intercept. Okay, and so they both go through for 0. Let's go ahead and turn that one pink, like we did last time. Okay, let's go ahead and turn that one orange. And the x is equal to 0, or the y-axis. Let's turn that one green. And our area is this little wedge right in here. Okay. Now, I know that my cross sections are going to look like this because they're going to go perpendicular to the x-axis. But my s of x, basically my expression for that length, for the side, generically the side of those cross sections, the place where the cross section hits the region, is not going to be either one of those, but their difference. Okay. Now I know that the orange one is it's more positive, it's on top, so it's going to be the more positive minus the less positive, and we get 4 minus x minus 2 minus 1/2 x. That winds up being 4 minus x minus 2 plus 1/2 x, or 2 minus 1/2 x. So, oddly enough, that is going to be exactly the same as if they were down here, which should make sense since basically this linear is basically that one multiplied by 1/2. But that is my s of x right there. I know that when I'm dealing with this, I need to do my constant out in front, limits of integration, s of x needs to be squared times dx in order to basically get the area of the face of that cross section with my s of x squared times my c, and then the width of those cross sections being dx. Now my c in this particular case is pi over 8 because it's semicircles. We've already gone over that in the last video. I know that my limits are going to be 0 to 4, just like they were in the last problem. My s of x is going to be 2 minus 1/2 x squared dx. Now, if you don't like the prospect of foiling that with a fraction in it, I've already told you that this linear was half of this. So you could actually represent it like this instead. And let me go ahead and draw a dividing line right here. If 2 minus 1/2 x is really 1/2 4 minus x, then s of x squared is 1/2 4 minus x, the whole thing squared. And by rules of exponents, I can actually call that 1/4 times 4 minus x squared, right? Well, all that is the previous one. I'm going to have exactly the same integrand. I simply need to pull an additional 1/4 out in front. And so this can wind up being pi over 32 from 0 to 4, okay, of, x squared minus 8x plus 16 dx. Now, I happen to know the value of that integral. That was exactly the integral from my last problem. It was 64/3. And so this one just happens to be pi over 32 times 64/3, 2 pi over 3. Okay. Now, basically part of the reason why it's smaller in volume is because it's a smaller region. But you also have to take into account the fact that semicircles are a smaller cross-section than the squares in which they can be inscribed. And we saw that in the last video, right? A semicircle is less than half of the corresponding square that would be the square cross section for the identical s of x. Okay. Now let's go ahead and move on. I think we have time for one more problem before gets unnecessarily long. Let's go ahead. Oh, I like that one. Y is equal to x squared. Y is equal to 1/2 x cubed. And the cross sections are isosceles triangle with the hypotenuse down. Now that means that my constant out in front is 1/4. Now it's going to be perpendicular to the x-axis. Again, these two functions and the region that are going to be between them can be represented. Okay. Let's go ahead and 1/4. Okay, and basically we have the parent function of quadratics. Comes down here, over 1, up 1, over 2, up 4, over 3, up 9. And then, of course, 1/2 of x cubed. Now, it's going to come through here. And it's going to hit that point, but then it's going to coincide with my quadratic. And so this winds up being just kind of weird. It's too thin for me to actually color code all of them, but it's this region right in here. It's really, really, really thin right in there, okay? But I still do have an area. I still can reasonably talk about cross sections. And so let's go ahead and set it up. Now, obviously, my limits of integration have everything to do with points of intersection, which, you can read them off the graph, or you can recognize the fact that it's 2x squared minus x cubed, right? Multiply by 2 and then subtract x cubed from both sides. Factor out an x squared, and I have 2 minus x, and therefore x is equal to 0, and 2 are my points of intersection. 0, 0, and 2, 4. I know that my limits of integration, therefore, are 0 to 2. I know that my constant that goes out in front is 1/4, and I'm going to go ahead and the difference between those is going to be my s of x. Now, it's the quadratic that's on top for that brief moment between 0 and 2. And so it winds up being x squared minus 1/2 x cubed, and I'm going to square that, which is of course going to be a little bit ugly, but I mean, you can use it you can basically square it in its factored form if you want. Notice that you could basically do that, and if you wanted to, without multiplying it by 2, you could have the x squared and the 1 minus x over 2. And that would basically, if you wanted to square that, it might actually be a little bit easier. Or you could recognize the fact that this right here is the same thing as if you had pulled out a 1/2, right? And if you factored out the 1/2, so you could actually, use that expression right there and square that. Now, that's going to be a little bit easier to square. And then, of course, what you have to do is this will turn into a quadratic, and that will be, basically, when that's squared, it'll just distribute across. And when that's squared, it can be pushed out in front to meet up with the 1/4 that you already have there, okay? Now, and you don't have to do it that way, but basically, it's just every once in a while I like to remind you of the things that you can do in order to make life easier for yourself, because the more often I remind you of these things, the greater chance you have of actually picking up on them and doing them yourself at some point. I'm going to do it by the calculator, though, okay? Just because, time issues, and I've already done a couple by hand. Let's do our integral. Oops, let's go ahead and first put our 1/4 out in front, and then we'll integrate from 0 to 2, and it was y1 was our x squared. Actually, let's go ahead and insert a parentheses right there, since we're going to be squaring this difference. And then minus y2, close parens, square it, and then plop an x out there for your differential, and boom, that is a really small volume. And it should be, because it's a really small region, right? 0.076 is the approximation of that region. Now, is it possible that that actually is a rational number? Yes, and it is. It's actually 8/105. If we had done it by hand, we would have gotten that, okay? So that's three problems, and we did two of them. Two of them were where the s of x was the difference between two functions, so I think that was helpful. We're going to do a couple more in the next video. I don't know how many videos I'll do. We'll just kind of play it by ear. I may just do one more and then see if y'all request any after that. I don't want to multiply work for myself unnecessarily. But I do, on the other hand, want to give you what you need and what you want. So please do communicate with me on that front. Yeah. Okay. Well, I'll look forward to hearing your questions, queries, or whatever. Just contact me when you need me. Bye.